In this video, we're going to introduce the process of Lagrange multipliers and its concepts, and the association with Lagrange multipliers is with constrained optimization. And when we have a constrained optimization, we have our optimization function, and we have a separate equation that represents a constraint or a limitation on the values we can pick for the function itself. We capture that here by calling the optimization function our usual f of xy, and the constraint is broken into or written in the form of an equation with a function. So it's important to note that this is a function. There's no equals on the other side, whereas the constraint is an equation with the g of xy on one side equals some constant. The interesting idea there is that this is not only an equation, but it can be considered a contour for the function g of xy. And this would be one single contour for g of xy. We're going to look at a geometric view, looking at a contour diagram of this idea as a constraint, combined with the contours on the function itself, and see how they relate. We'll see that on the next page. Now this diagram here has quite a lot going on. Let's start by focusing on the black lines. And that simply means the contours like this, associated with height 10, 20, 30, 40. And what we see from that is that we have a general uphill direction for the surface itself. If we were to imagine this viewing down from above, we'd see that the top of a hill is over here, and then we go down as we go this direction, back up, we go this way. And that would tell us that maximum values will tend to be at this end. Minimum values will be down here, but there's no single minimum showing here. What we're adding to that is a constraint. So there's only some x and y values that we're allowed to pick, and they're defined by an equation, which we can also think of as a contour. These are all interchangeable ideas when we have this form. We see that graphically as a contour. It might be a very different shape because this equation might look nothing like our function. Totally fine. So what we're allowed to do is pick values only on the blue line. So of all the x and y's in the entire plane, the only ones we can choose are on that blue line. All right. Well, that makes the problem a little more interesting, and it actually makes it solvable, because if we imagine this is the uphill direction for the general shape of the surface, but we imagine this is a road that we can drive on, as we're driving along the road, we're looking for the highest possible point, and we can see that we're at height 30 here, looking at the contours in F, then we'd be at like 35, 39, and then we would just touch the contour at height 40. And so on the constraint, this would become our maximum value. Out of the road we're driving on here, out of all the heights we can reach, I can just touch height 40 here, but there's no way on the blue line we're ever going to reach height 50. We can see that the blue line and the black line for height 50 don't intersect. We can then go in the other direction and imagine driving along the road. We'd be at height 40, then down to height 30 here, and then we would drive down further, and in this case here we would just touch the height 20. We can't get as far as 10 because our constraint doesn't let us go there. But on the constraint, this would be the lowest possible height of the function. But on the constraint, this would be the lowest possible height of the function we can reach. So we have a minimum, we have a maximum, but there's no critical point type stuff happening here. There's no derivatives equals 0 at those 2 points. So we're looking for something a little different in terms of the characteristics of those locations. The magic here is going to be to return to gradient vectors, but to do so in a new way. Let's imagine the black lines here. So on the contours of F, we know how the gradients work. If we pick a point on a contour, we're going to draw a gradient vector, which is going to be perpendicular to the contour and which points uphill. So out of the two perpendicular directions, the gradient points this direction. And we could do that over here as well. And we could do it over here as well. And that's totally reasonable. Of course, these points aren't actually relevant because they're not on our constraint. So let's draw the ones, say, on the constraint. And maybe over here and over here as some easy grounding points. And at the minimum too, why not? Pointing uphill. There we go. Well, what about the blue line, the constraint itself? We can think of that as a function equaling a constant, which is both an equation that defines a curve or one contour out of many. And if we take that as our interpretation, we can imagine that if we picked a different value for this number on the right-hand side, we would get almost the same curve, but in a different location, here a little inside or a little outside. Now what does that mean? Well, it means that we could define a surface here. Let's say this is the peak, then going down, then going down. At each location of the blue line, we can define a gradient of g, which would be perpendicular to the blue lines and pointing in the uphill direction. And we can see that that would point inwards here. If we did it here, it would point in this direction. Did it here, it would point in this direction. What gets interesting is if we scope down to our local minimum here, well, minimum on the constraint, notice the blue line is going to be the same as the black line in terms of its direction. Because we're just touching this black line here, the slope of the blue and the black are the same, so if we draw a perpendicular vector there, they're also going to be pointing in the same direction. Now what about the maximum? Take a look here. If we go perpendicular to that, it's going to be pointing inwards, but again, along the same line here. Redraw that to make it more clear. Redraw that to make it more clear. The vectors here are along the same line. They can be parallel here, but possibly in opposite directions as well. And that's interesting. If you think about what's happening here, the blue vector and the black vector are pointing in different directions. But for some reason at the most interesting points, this minimum and this maximum, we get the gradient vectors of the g and f pointing in the same direction. Now why might that be? Well, if you think about the black lines, imagine that we're talking about our surface now of height 10, 20, 30, up to 60, and we're driving along this road. If we're at this point here, what we have is, if I can follow the black line would point me in the uphill direction, then I would be going uphill. But I can't go quite in that direction, but I can certainly go in a direction related to it. In other words, I can head somewhat in the uphill direction by following the constraint, by following the blue road here. And what that means is I'm not at my highest point because there's somewhere I can go that's still uphill. And you can continue that pattern as you go through this entire pathway here. Even up to here, the uphill direction would be towards this side here, but the road will take us a little bit in that direction. It's not great, it's not the most efficient uphill direction, but it's still in the uphill trend until we reach the absolute highest location. And at that point, what we have is the uphill direction is here, but the curve that we can move on can only move perpendicular to that. And if we can only move perpendicular to the gradient, that means we're not changing height. This is another feature of contour gradient relations. And so we can't go any higher. Literally at this point on the blue line on the road that's defined by that curve, we cannot move in the uphill direction at all. The best we can do is move downhill, or technically flat if we move parallel to the blue line. And so that means somehow we've gotten as far in the uphill direction as we can get. And then we have this nice relationship between the gradients because both gradients are perpendicular to both contours. The same kind of logic applies at the bottom end. We're driving downhill, downhill, downhill. Again, if I wanted to go really downhill, I would go in this direction perpendicular to the black lines. I can't go that way on the road, but I can at least go some amount in that direction, some little bit downhill direction, even though I'm going mostly perpendicular to it, until we reach the most interesting point, the absolute lowest point on the road. And at that point, downhill would mean going this way, but we can only go in the direction perpendicular to it. So we're going to stay on a contour. We're not going to be able to go down any further. Now that's a ton of conceptual theory looking very heavily at one contour diagram. The key thing that we need to walk away from this with is this condition. If we label these points capital M and little m, then what we have is that the gradients are parallel. The gradient of f at the maximum point is parallel to the gradient of g at m, and also at the little m. It would be tempting to say that one time they're anti-parallel, like pointing in opposite directions versus the same direction. It turns out in practice, depending on how you write your formulas, they can go either way. The max or the min can show up as this scenario or this scenario here. So it's enough to say that at a point of interest, the two gradients will be parallel to one another. Our next step is to formalize that into some mathematical equations that will let us solve for those locations in a particular example.